Okay, let's talk about some basic matrix operations that are going to be fundamental in the applications that we have in the next little bit when we look at recasting things like systems of equations into code. This concept of matrices becomes fundamental. So let's talk a little bit about what is a matrix at the beginning, right? So let's focus on this term. What is a matrix? A matrix is a collection of elements into an array. And this array has a number of rows and it has a number of columns. And matrices are represented typically as their dimensions in terms of rows and columns. So, and it's always in that form, row times column. I remember this by RC. Let's do a capital R, so maybe it's a little bit easier. RC, so each element is then indexed by its given place in the matrix. So for example, if I wanted to know what is this element, it's in row 2, column 2, or this element here is in row 1, column 2. So rows and columns, collections of elements. Each of those then has its own ability to be carried out in terms of mathematical operations. So let's take a basic example here. Let's say I have a 2 by 2 matrix that's represented 1, 2, 3, 4, and I wanted to do basic addition. So in matrix addition, we want to make sure that both of the matrices that we're going to add have the same elements or element-wise identical. So this is a 2 by 2, so this is also a 2 by 2. And if I had another one that was, let's say it's identical, 1, 2, 3, 4, of course, then I would carry these out element by element, meaning that this element would be added to this element. So it would be 2, 4, 6, 8. And if I want to do the same thing for subtraction, it works the same way. 1, 2, 3, 4, minus element by element, 1, 2, 3, 4. This 2 by 2, as you might imagine, I've got a 0 by 0, 0, 0. Matrix, don't need a comma there. All right, 0, 0, 0, 0. Pretty straightforward. So does both addition and subtraction work with a matrix the same way that it would work with adding and subtracting real numbers? It looks a lot like the substitution methods that we just used in our review of systems of equations. However, let's take this one step further and let's talk about multiplication. So what if I had a matrix, that same matrix we were just looking at, and it had the element values 1, 2, 3, 4, and I'm going to multiply it by some other matrix. What does that equal? And how do you perform that operation? So with multiplication, as you might imagine, it's going to work a little bit different than it is with addition. And that difference, in this case, we're going to put these two values in here. -3 and 4. And you might recall that from our previous example, those were the solutions when we used substitution for x and y. And I'm going to show you how we carry out this operation, this 2 by 2, this 2 row by 2 column, by this 2 row by 1 column matrix operation. So first thing that you need to know in terms of a rule of thumb for matrix multiplication is that the two inner values, the matrix on the left, the number of columns, has to match the matrix on the right's number of rows. So these two numbers, 2 and 2, have to be the same. And then the resulting matrix is going to be the values of the outer values. So the number of rows of the matrix on the left will be the number of rows of the resulting matrix, and then the number of columns on the right will be the resulting matrix number of columns. So when we carry out this operation, we should have a value over here that results in a 2 by 1 matrix. One aside is that any matrix that has a single value here and that it's got one row or one column is actually commonly referred to as a vector. So a vector is a row of objects or a single column of objects. Sometimes you'll hear people refer it to as a row vector or a column vector when they're doing mathematical operations. Okay, all right, with that, let's show you how this calculation would actually be done. I'm going to clean this up a bit here so we have a little bit more space. Okay. All right, so the way matrix multiplication works is that you go row by row on the left matrix and then column by column on the right matrix. And then you multiply elements with each other, and then you add them together. And this will be convenient when we do these mathematical operations, and you'll see why here in just a moment. So I take this 1, and I multiply it by this -3, and then I take this 2, and I multiply it by this 4. And you can see with just this basic set of operations, this is why we have you have to have a matching number of rows in one and a matching number of columns in the other, because this 1 and this 2 have to be matched against the same number of elements that are in this column. So that would give me -3, that's 1 times -3, plus 8. And then I would do the same thing down here, 3 times -3, and 4 times 4. So 3 times -3 is obviously -9, and 4 times 4 plus the 16. Right, and then of course if I just carry that through, I've got 5 and 7. Right? And of course 5 and 7 we remember from before. This is a 2x1 matrix, but it is also the original answers to the system of equations that we had before. Now this matrix calculation can be efficiently implemented into code if we re-represent these matrices. Instead of by their collection of elements, we represent them symbolically. Let's say this larger matrix C on the left I call X, this smaller matrix C, I call A, capital A, and I call this smaller matrix C X equals to B, which are the solutions. And A and B are values, and X is a variable. And in this case, B is a vector and X is a vector because they each have one column. And then A is a matrix of some symmetry relative to X. And we'll look and see how we can take advantage of this formulation, A, X equals to B, in the next video.